Okay, so quick review of reviewing the general rules for assigning oxidation states, because if you can't assign oxidation numbers, you're going to have a lot of trouble here in redox. Remembering general rules here, elements or diatomic elements, anything in elemental form gets assigned an oxidation state of 0. Ions usually follow their oxidation state. Their assumed charge, like the alkali metals, group 1, are always +1. The alkaline earth metals are +2, and so forth. Aluminums in group 13, it's +3. And then, of course, metals combined with, non-metals combined with metals, they follow their normal oxidation states, like group 15's -3, group 16's -2, and the halogens are -1 there. Hydrogen's always +1, except for when it's with metals. So hydrogen pretty much is usually with non-metals. It's going to be +1. It's a rare occasion that you'll see it bonded to a metal. In that case, the metal is going to carry the positive oxidation state, and hydrogen will be a -1. Oxygen, for our purposes, because I am not going to give you any peroxides, is always going to be -2. Which fits with the idea of it being in group 16, because that group goes to -2. Don't forget, neutral compounds always add up to 0. And then polyatomic ions add up to their charge, their formal charge, when assigning oxidation states. Because we're going to be doing a lot of assigning now. I know we got through most of this last time, but I'm just going to run through a few of them just to make sure. Like, for instance, on all of these ones that have oxygen, like I just told you, they're all going to be -2s because none of these are peroxides. So we could go through and assign them all -2, like so. And you can do that. You can go through and assign the ones that you do know. Like, for instance, the hydrogen's +1 here. Hydrogen's going to be +1 here because technically it's bonded to the oxygen there. We'll talk about the polyatomics in just a second. This is elemental chlorine 0. This one's going to follow its oxidation or its formal charge number. Strontium's group 2, and it's an ion there. Now looking at some of these other ones, remember when you have two nonmetals here, which technically are not ions in the normal sense. However, we assign them oxidation values or oxidation numbers to keep track of the electrons. Because when the covalent compounds, their bonds break and they form new bonds, you do have a reshuffling of the electrons. And this is a way of keeping track of how the electrons are reshuffled. Because technically, if it's forming a covalent compound, it's going to share those electrons. It's not going to transfer them. But we do have to keep count, and that's the whole point of assigning oxidation numbers. So here, if this is a 5 and it's -2, so that's a total of -10. That means this one has to represent +10 because it needs to add up to 0. So in this case, the nitrogen's going to have a +5 for its oxidation state. The only time the nitrogen's going to follow its normal group charge is when it's in the second half of the compound, like the oxygen is in the second half of the compound here. Same thing here. This is a 2 oxygens at -2, so that's -4. That means the nitrogen's a +4. Now one that has 3 elements in it. Usually you automatically know the first element is going to follow its normal ion charge. And then, of course, oxygen here, since this is polyatomic, this would be 3 times -2. So that's -6 for the oxygens. Hydrogen's +1. So to make this add up to 0, that means the chlorine is carrying an oxidation number of +5. Now for the ones that have polyatomic ions or actual charges on there. So There's actually two ways to look at this one. I know I don't think we got to the calcium nitrate last time, but you can pull the nitrate out and figure out its oxidation numbers separately. Like for instance, nitrate you know is NO3 minus. Well, if you know that that's NO3 minus, you still know that oxygen's going to be -2. So together that's a -6. And because we have a charge of -1 on the nitrate in general, that means the nitrogen here has to be a +5. Because +5 minus 6 gives you the -1. That's one way to do the nitrate. Pull it out from the compound, do it separately. So then this would be a +5 that way. The other way to do it is to do all the distributing with the parentheses, which gets a little bit more math heavy. We know calcium is in group 2. It's an alkaline earth metal, and the group 2 metals are always +2. So I know this one's +2. I know the oxygen's -2. So in the nitrate, there's three oxygens in the nitrate itself. And so therefore, there's a total of 6 oxygens because we distribute this 2 here. So 3 times the 2 here gives us 6 total oxygens. And if each one's -2, then the oxygens total to a -12. All right, so this has to add up to 0. That means the 2 nitrogens, because if we distribute the 2 to the nitrogen, that means there's 2 nitrogens. That has to be a +10. That's the +2 of the calcium, +10 from the nitrogens, and then the -12 from all the oxygens. Still, but there's this 2 outside, so that we know there's 2 nitrogens, so that 10 divided by 2 is where you're going to get your +5. So you can do the distributing way, or you can pull out nitrate separately. I do that. I pull out the polyatomic separately and figure it out. Either way will work. Kind of the same thing here with the iron 3 hydroxide. Hydroxide is OH minus. So hydrogen's +1, the oxygen's -2. That's where that minus sign comes from. But if you distribute it, this would be, you know, hydrogen's at +1, 3 of them. So that's +3. Let me move this over. So total would be +3 from the hydrogens. 3 of the oxygens, those are -2. That's going to be -6. So the iron then has to be a +3 to make it add up to 0. Like so. Last 2 over here have charges on them, so you make them add up to the charge. Oxygen's -2, so this is a total of -6. That means the carbon has to be a +4 to make it add up to -2. So in this case, carbon and carbonate's +4. And the tin, I don't know, this is a polyatomic ion with tin. This case, second position, it's going to follow chloride's normal charge, normal oxidation number of -1. Needs to add up to -1 because of the minus on there. So this is going to be a -3. So in order to make it equal -1 here, this has to be a +2. Now, once again, like I said, assigning oxidation states is part of the issue. You got to make sure that you assign them correctly, or you're going to have trouble down the road. All right, I think we got here too, talking about the basics. Oxidation is losing electrons, becoming more positive, increasing the oxidation state. So this is going to be more positive. Looking for the charge change to increase, or the oxidation number to increase. Reduction has a decrease in oxidation state because you're gaining electrons. This is going to become more negative, like so. Remember, electrons, that's how we write them, E with a minus, because they are negatively charged particles. So if you add them in, you become more negative. If you lose them, you become more positive. Now, one of the sayings you can use is Leo the lion says grr, because you lose electrons in your oxidation, gain electrons, you're doing reduction. The other one you can use that people use frequently is oil rig. Oxidation is a loss of electrons. Reduction is gain of electrons. Either one you choose to adopt to help you remember is fine with me, because you just need to be able to know which way it's going for oxidation and reduction. All right, let's talk about the agents. The agents are opposites. Just going to go with that. They're going to be the opposite. So, oxidizing agent is the electron acceptor. It helps the other element be oxidized. Remember, this is a paired situation. So, one element's gaining electrons, the other one is losing electrons based off of the counting of the oxidation states. So, if one particular element is being reduced and gaining electrons, it is now causing the oxidation of the other element. So it would be considered the oxidizing agent. The element being reduced is going to be found in one of the reactants. That reactant that has the element being reduced is the oxidizing agent. It is causing the oxidation of the other element. Opposite's true for reducing agent too. So the element that's being oxidized that gave away those electrons is now causing the reduction of the other element, and therefore it'd be the reducing agent, the electron donor, giving those electrons away. Helps the other element be reduced, this compound that contains the oxidized element in it. So if we're looking up here at our two reactants, you can see that zinc goes from 0 to +2. So it's becoming more positive, it's being oxidized. That means zinc is the reducing agent, because it's causing the reduction of the hydrogen. So the hydrogen goes from +1 to 0. It is being reduced. So the hydrogen is causing the oxidation of the zinc. So that's why the hydrogen is the oxidizing agent, because it's the element being reduced. All right, so now find the element that's oxidized, the elements that reduced, and we're going to determine the oxidizing and reducing agents here. Now up here, you can see that they didn't separate the sulfate into two separate boxes. You see sulfate on both sides like this. What's going to happen here with the sulfate being on both sides? Remember, sulfate is SO4 minus 2. You could go and calculate the individual sulfur and the oxygen's oxidation states, but you really don't need to. Okay, because it's going to be SO4 minus 2. So we're just going to put minus 2 in here for the entire sulfate, like so. Unless otherwise specified to identify sulfur individually and oxygen individually, you can do it that way. You can go based off of the polyatomic ion charge. From there, the rest of it should be pretty simple. What is the oxidation number of the zinc over here on the reactant side? What's that going to be? What's that oxidation number? Anything in its elemental form is automatically by itself, element 0. Thank you. That one's 0. As you can see over here, copper's by itself, elemental form. That's going to be a 0 too. Didn't forget that one. Now we look to our compounds. And if sulfate's minus 2, because we know that from looking up our polyatomic, what does that mean this copper in the compound is going to do? What's its oxidation number? It's going to be +2. Very good. What is this zinc's oxidation number going to be? Also +2. Very good. Now we can look and see which element's being oxidized, which element's being reduced, and then we will go and figure out our agents. So zinc goes from 0 to +2. You can see it starts out at a oxidation number of 0 and then it ends up at +2. Is it being oxidized or reduced? Becoming more positive or becoming more negative? Oxidized, good. It's becoming more positive, so zinc is being oxidized. Then we look up here and look for the other one that's changing the charge. If you look here, the sulfates don't really change. We call them spectators, just like before. Ones that don't participate in the reaction or the transfer of electrons or the reshuffling of the electrons, those are spectators. They're not really playing a role here. So the other one then is the copper's going from +2 to 0. Is that becoming more positive or more negative? More negative, so that one's definitely reduction. One more key thing to talk about in terms of the agents. The agents are always one of the reactants. You have to write out the entire reactant. But you look here, if zinc's being oxidized, all right, that means the reactant that has zinc in it is going to be the reducing agent. So the reactant that has zinc in it is just zinc. So it is going to be the reducing agent. It's causing the reduction of the copper. However, looking here at the other one, the full reactant that contains the copper is copper 2 sulfate. Copper 2 sulfate, the copper is being reduced. So the entire reactant is considered the oxidizing agent. You would have to write down the entire reactant that has the element being reduced. That reactant is causing the oxidation of the zinc. So the copper is causing the oxidation of the zinc, but it's the entire reactant we write down as the agent. All right, your turn. Time to do some practice here. First, fill out the oxidation numbers. Got to start there, then decide which element's being oxidized, which one's being reduced. Okay, let's assign oxidation numbers. What do we assign for chlorine, Cl2? What are we going to put for that one? What's its oxidation number? It'd be 0 because it is elemental chlorine. Very good. How about the potassium in KBr? What's its oxidation state? It is +1. Potassium is an alkali metal in group 1. It's going to be +1. How about the bromine here in KBr? What's its oxidation number? -1. It's a halogen. Very good. So it's going to be -1 there. All right, so potassium still +1, alkali metal. Chlorine here, also a halogen, so what would its oxidation state be? -1, and then Br2, elemental bromine, a 0. Very good. All right, so now we have to look for which elements are changing in their charge. The chlorine starts at 0. And it goes over here to -1. So is that one being oxidized or reduced? Good, chlorine's being reduced. Like so, exactly right. Which other element is actually changing in its oxidation number? Bromine's changing, very good. Bromine goes from -1 over here to 0. So bromine, obviously, if we've already identified chlorine as being reduced, it must be being oxidized. It is a paired deal. Very good. That means the case their charge is not, or their oxidation number is not changing, that would be, potassium would be considered a spectator here, not really participating in the redox. Now let's look at the agents here. Bromine's being oxidized. That means the reactant that has bromine is causing the reduction of the chlorine. So bromine would be, or which reactant? The KBr. That's bromine's being oxidized, that means the KBr is the reducing agent because it's causing the reduction of the chlorine. And that means too, the oxidizing agent here, okay, because chlorine is being reduced, the reactant with the chlorine in it is going to be the oxidizing agent because it's causing the oxidation of the bromine. So this would be Cl2. For the agents, you need to write out the entire reactant that is for the agent. All right, one more fun one. Give you a couple minutes. Sign oxidation numbers. Okay, so what I would suggest to you, especially for something like this, start with the ones that you automatically know. What's the oxidation number of oxygen? -2, so you can fill all those in. -2, -2, -2. That's easy enough. What other one up there is definitely pretty obvious? I2, right? Good. I2 is elemental form of iodine, so that's going to be 0. What else do we know about hydrogen when it's with all nonmetals? What's its oxidation number always? It is +1. Very good. So we can fill those in pretty easily. +1, +1. That leaves only a couple that we have to figure out from actually calculating here. So here, I'm going to start over here with the iodine. So we multiply the 3 times the -2, that's going to be -6 for oxygen. This is +1. So R needs to add up to 0 in this particular case. This is an iodic acid. Iodic acid, the iodine is going to be a +5. That's +1 -6. That means the iodine is holding an oxidation number of +5. The nitrogen here, looking at the nitrogen, this is 2 times the -2, so that's -4. That means this nitrogen has to be +4. And then looking at the nitric acid, HNO3, times the 2 gives you -6. This is still +1. That means the nitrogen has to be a +5 there. Now, looking here, which ones are our spectators? Which elements are the oxidation numbers not changing? Because it's best that we cancel those out and not pay attention to them. Which ones aren't changing? Hydrogen. What's the other one? Oxygen. Very good. These ones are spectators, so you can ignore them. Okay? Now, that means nitrogen's +5 going to +4. Is nitrogen being oxidized or reduced? Reduced. Very good. It is becoming more negative. The iodine starts at 0 and goes to +5. So it's definitely becoming more positive and gaining an oxidation state. I is being oxidized. Now our 2 agents. 2 reactants here. Well, I is being oxidized, so the reactant with I is going to be the reducing agent. The reduced nitrogen, the reactant with that, is going to be the oxidizing agent. So the nitrogen in nitric acid is causing the oxidation of the iodine, and I2 is causing the reduction of the nitrogen there. All right, so that's one thing that you'll have to be able to do is assign oxidation numbers, figure out what's being oxidized, figuring out what's being reduced, and the agents. The next thing you'll have to be able to do is write out the balanced half reactions. You have an oxidation half reaction, you have a reduction half reaction, where we're also going to be inserting the electrons. We're going to be balancing out the charges with the electrons. Figuring out what's being oxidized, write out the reactant and product of that element. You might need to break it apart into its oxidation state. If it's in a compound, you have to break it apart like it looks like an ion. And you would do the same thing for reduction. And you balance those. Then for each half reaction, you're going to add electrons to either side to make the charges equal on both sides of the arrow. Now, what you'll notice when you add in electrons to the oxidation one, if you're adding electrons to the oxidation, it's going to end up being a product. Because we know oxidation is a loss of electrons, that means the electrons have to be being given away. So they have to be part of the products. If your element is being reduced, that means you have to add in electrons. Electrons are being gained, so that means for reduction, it's going to be part of the reactant side. Remember, this happens in a pair. One has to give away, one has to take. So you always have oxidation and reduction occurring at the same time. All right, for example up here. Go ahead and assign oxidation numbers up here. Pretty easy. Elemental lead, elemental copper. I always put those in first. This is metal, non-metal, so chlorines are -1 because they're halogens. And then that means here, if there's -2, this is going to be +2. This is -2, so this is going to be +2. Looks like our chlorines are spectating, so we don't have to worry about them. But we look at our lead, starts at 0, goes to +2. Is lead being oxidized or reduced? Oxidized. So we're going to write out the half reaction here. We have Pb going to Pb2+, like so. Now, over here on this side, the charge is 0, and we know that it's being oxidized, so that means the lead's giving away electrons. But we need this side to also be 0, because it needs to be balanced charge. So what do we add in to balance it? Make that charge 0 on both sides. Well, all we have to do is add in 2 electrons. Because the 2 electrons represent a charge of -2. The Pb has a +2. So +2 -2. Essentially, this is, the +2 and plus the -2. This is going to represent that 0. As you notice, as stated before on the previous slide, the electrons are part of the product. They are written over here as a product. Now let's look at the other one. We said chlorines are spectating, so copper is being reduced. Copper is being reduced. So we're starting out with, now the copper is in this compound with a +2. So we're going to write that out as Cu2+ right here. I'm going to leave a little space, and you're going to see why. And we're going over here to Cu. So to make this add up correctly, where do we need to put our electrons? Took 2 electrons to be given away from lead. So now we need to put them on the reactant side, good. So we're going to put the 2 electrons here. So this now adds up to 0. And then, of course, the copper is 0. Like stated before in the previous slide, the reduction half reaction is going to have the electrons as a reactant, as it's gaining those electrons. This one's particularly easy because everything in the balanced reaction is a 1-to-1-to-1 ratio for the molar relationship. Looking at the next one is not going to be so easy. Here, it's not 1-to-1-to-1, so we're going to have to do a little bit of balancing as well as adding up our electrons. But quickly assign oxidation numbers. What are the oxidation numbers of the nitrogen and the hydrogen on the reactant side? Both over here should be a what? What are those oxidation states? Zeros. Yes, that's easy enough. Now this one's a little tricky. Hydrogen is with nitrogen, which happens to be a nonmetal. What is its charge? What is its oxidation number in that case? It is +1. So this is +1. There's 3 of them. That means the nitrogen is a -3. And that's a weird one where you're actually writing the oxidation number of the -1 first. That's a rare case, by the way. Doesn't happen very often. But now we look 0 to -3 for the nitrogen. Is that one being oxidized or reduced? Oxidized or reduced? 0 to -3. Reduced. Okay, so I have to start over here. So where it's going to get a little crazy here because we have N2. We have our N2. And we know we're going to be adding in a certain amount of electrons. We just don't know what they are yet. But that's going to produce over here 2 of the nitrogens at -3. So 2 of the nitrogens at -3, like that. So, in order to make that work, how many electrons is that? Because this is 2 times -3, so this is -6. How many electrons do we need to put there to make them equal on both sides? Because we know this nitrogen, it's a 0. So all we need to do is add in electrons. How many electrons do we add in to that side to make it also the left side, the reactant side, have a charge of -6? Electrons are negatively charged particles, so how many of them do we need to make -6? We need 6, exactly right. So 6 goes here. So that's going to be -6 to -6. The charge doesn't have to be 0, it just has to be equal on both sides. So we have -6 on the left, -6 on the right. Has to be the same. Let's look at the oxidation half reaction. Very good. 0 to +1, but there's 3 of them. So we have to keep our 3H2 here. And we're going to 2 times the 3. So how many H pluses are coming out of that ammonia to the right? Each ammonia has 3 H's that are +1s. So that's a total of how many ammonia? That's going to be 2 times the 3, 6. So we get 6 H pluses out of that ammonia. And we know that oxidation side is going to have the electrons over there on the products. The oxidation has electrons on the products. Now the hydrogen, regular hydrogen is just 0, so that's 0 right here. So how many electrons do we add in to make the +6 H's equal 0? It's going to also be a 6. So you can see the charges are equal on both sides of the half reactions, like so. Now it's going to be your turn to try. Practice. Go ahead and see if you can do it. And if you get done with this one, move on to the next one, the last practice. And we'll go over that We'll go over both of them and say about 5 minutes. So go ahead, try them on your own. All right, oxidation number for magnesium. Who's got it? Magnesium? +2, thank you. It's going to be +2 there. It's going to be +2 there. How about iodide in the magnesium iodide? Halogen? -1, thank you. All right. Elemental chlorine 0, elemental iodine, and another halogen there. Good. We got our oxidation states. Magnesium spectating up here. We don't need to concern ourselves with magnesium. But let's look at the iodine. It goes from -1 to 0. Is that the oxidation or reduction? Oxidation. So we'll start here. Now remember, there's 2 of them in this compound, and we're going to write it like it's oxidation state. So you would put 2I- there, like so, because there's 2 of them in the compound, and they're both representing -1 oxidation states. Now over here, it's going to this product, I2. All right. And where do our electrons go, and how many do we need to make it balance? This is a -2 here from that. Right now, we just have the 0 from the iodine. So where do our electrons go? And how many electrons do we need? Where do our electrons go, and how many do we need? Oxidation, they're always part of the what? Product, very good. So we're going to put the electrons over here. How many of them do we need to make it balance out to being a -2 charge? We need 2. So we put a 2 there. Now the charges are equal. Very good. That means over here that the chlorine must be the reduction half reaction. Starting out with our Cl2, going over here, now there's 2 in the compound like before, so it's going to be 2Cl- like so. So this is -2 over here. And we know in the reduction, we're going to be putting the electrons over here. How many electrons do we need to make it balance? How many electrons? Remember, we need a -2 here. And the chlorine's representing a charge of 0, so we need 2. We need to put a 2 there, so that's -2, like so. A little bit more challenging. Now it's going to get even harder. Let's look at this example. This one's kind of fun. We've got iron is 0. Silver is 0. Nitrate we're going to keep together at -1 because that's what the block up there says. And anyways, nitrate will be +5 for nitrogen and -2 for oxygen, so we'll just use the formal charge on the nitrate. So that makes silver a +1, because silver is always +1. But if nitrate's -1, silver's got to be +1 there. And then this 3 out here tells me the iron is going to be +3. All right, which one is the oxidizing element? Which one's being oxidized? Iron, thank you. So iron's over here, starting here. It's going to go to the Fe, and it's in the compound, so we're going to write it as the oxidation state, like so. That means we need to add in a certain amount of electrons. So if this is 0 over here, because elemental iron, how many electrons do we add in to even out that +3? 3 electrons go here. Like so. So this is going to be 0 over here. Now for the last one, we've got silver, because the nitrates are spectating. So silver is going from +1 to 0. Now don't forget the balancing. How many silvers do we start with? Silver +1s, because of that coefficient. How many silvers? 3. We need 3 Ag pluses to begin with. Now we know we're going to be adding in a certain amount of electrons here. And then we're going to go to 3 of our Ag elements. So over here, this is 0 because that's what it is. We're adding in our electrons. That means this has to be a 3. So this ends up being 0 as well, making that charge equal on both sides. So that's balancing half reactions. Lots of fun.